Hello and welcome to the first video of the first module of your physics class. Now, just like a whole bunch of other physical science classes that I'm sure you've taken already, we're going to start out with units. Then we're going to talk a bit about dimensional analysis. That's basically how we can use units to find out something else interesting, or how we can make units kind of guide us to the right answer. And then finally we'll talk vectors. We won't get to all these things in the first video, but that'll be coming up in the first module. So, units. You've probably noticed by now that science teachers really push units. There's a reason for that. It's not just so you can put something kind of nice at the end of your number so that you get full credit on a problem, even though, yes, that's what it is. Units are everything. Units are life. Think about it this way. The acceleration due to gravity of all objects, which we'll talk about in Module 2, so you don't need to know it yet, but it's 9.8 meters per second squared. And that 9.8 becomes kind of a magical number, except it doesn't actually mean anything without knowing what a meter is and without knowing what a second is. So every single constant we come up with in this class, it all goes back to units. So they are super important now and for the rest of your lives. Think of it this way as well. If I tell you that you owe me 200, it's going to matter a heck of a lot if I mean cents or dollars. So, at the end of this video, you should be able to answer these questions. What are the primary metric prefixes? We're all about the metric system here. What steps are necessary to convert from one unit to a different one? What kind of terms can be subtracted, added? What kind can be multiplied or divided? Before we even get into that, though, start getting comfortable with the idea of doing mathematics without any numbers. So let's say I give you a force, a centripetal force. It's mass times velocity squared divided by radius. Now, you don't need to know this term for centripetal force yet. We'll get to that in a different module, but I'm just using this as an example. Let's say I need to solve for velocity. I need to get real comfortable being able to solve for velocity without plugging in 3 for mass or 5 for radius, because then the mathematics becomes meaningless. So, solving for velocity, I'll just, let's see, divide out mass and multiply by a radius. And I'll do that on both sides of my equation. So that way on the left side, my radii will cancel out, my mass will cancel out, and I'm left with just a velocity squared. Okay, cool. Now all I've got to do is take the square root of both sides of that equation, and I've solved for velocity. Now, a lot of times in physics problems, you will be given actual numbers to plug in. I highly recommend you don't do it until you get to this last step, where you've got what you are solving for on one side of the equation by itself. Because if I get, let's say I accidentally put in 3,000 instead of 3 for the mass, oh, that's a problem. But at least I only have to tweak this last little part. Whereas if I shove 3,000 in here, at the very beginning, I got to redo the entire problem, and that is a huge pain. So start getting comfortable doing that. That was a bit of an aside. Let's talk units. Now, in America, we talk about feet, inches, pounds, yards, and miles, and that's what we're used to measuring things in, except scientifically, a lot of times that's not how it's done, and the conversion factors are so crazy. There are 12 inches in a foot, and there are 5,280 feet in a mile. That's just a lot of numbers to remember. I don't have time for that. So instead, we're going to do the metric system, and you've probably been introduced to the metric system by now. So I won't spend too long on it, but here are the prefixes that you need to know. Mega is times 10 to the 6, kilo is times 10 to the 3rd, centi is times 10 to the negative 2, milli times 10 to the negative 3, micro times 10 to the negative 6, and nano times 10 to the negative 9. There is a lot more than that, but that's what you're going to need to know from my class, at least. Now, this over here is what's called the metric staircase. You can use it if you want to, don't use it if you don't need it. But I find it useful, because if I start at one spot, let's say kilo, so kilometers, and I want to get to meters, then I just need to move my decimal point 1, 2, 3 spaces to the right, and done. If I want to get from meters to kilometers, I just move 3 spaces to the left, and done. Now this is really important. Let's say you're looking up 4.5 meters, and you want to convert it to kilometers. Well, I'll move 3 spaces to the left, throw in some extra zeros, and I get 0.00 0.45 kilometers. And that seems pretty reasonable. If I do that in the wrong direction, and I give an answer of 4,500 kilometers, which is not correct, then I'm going to be way, way, way off on any of my future measurements that involve that. Think of it this way. 4.5 meters, that can probably be laid out in a straight line on the physics platform and not run into anything. Now, 4,500 kilometers is 2,796 miles. That's the distance from Los Angeles to New York. So that's a huge difference. So do not go the wrong way when you are converting units. Take that extra bit of time, look at your metric staircase, make sure you're moving the decimal point in the correct direction. General rule is the bigger the unit itself, like a kilometer is bigger than a meter, the smaller the number that should be associated with it if you're converting. Speaking of more complicated unit conversions, you can assume that all units are a fraction with a numerator and a denominator, just like all numbers are. Take the number 2, for example. The number 2 is actually a fraction. That means 2 divided by 1. It has a numerator and it has a denominator. You can do the same thing with units. So meters per second, that's a speed or a velocity. It's got a numerator, meters, denominator, second. Cool. Now, lonely units, like a kilogram, just like 2 equals 2 over 1, a kilogram equals kilogram over 1, just to kind of help you with these unit conversions. From there, once you've got them set up all as fractions, look at where you're starting, what units you have to begin with, look at the final units, where you want to go, and then set up your conversion factors. Here's what I mean by that. Let's say you've got 28 centimeters equals how many meters? You could jump to the metric staircase, or you could set this up. I've got 28 centimeters divided by 1, then I multiply it by a conversion factor. 1 meter is up on top because I want to get rid of centimeters by putting it in the denominator. And I want to end up with meters, so I'm going to replace it there. Centimeters in the denominator cancels with centimeters in the numerator, and there we go. Now this number, 1 meter over 100 centimeters, because the numerator and the denominator are the exact same thing, 1 meter is 100 centimeters, all I'm doing is multiplying essentially by 1. And that doesn't change its value at all. And that's how unit conversions work. So I take 28, multiply it by 1 meter over 100 centimeters, which is essentially doing nothing to it but changing the units. And I end up with 0.28 meters. It works for more complicated problems as well. 14,322 centimeters equals how many kilometers? Well, I know how many centimeters are in a meter, and I know how many meters are in a kilometer. So I can just set up a multi-step. For the first step, I'll cancel my centimeters, and now I've got units of meters going forward. But that's not where I want to be. I want to be at units of kilometers. So I can set up another conversion factor, have meters down below, cancel it there, put kilometers up top, and boom, I'm at units of kilometers. Nice. Now, a lot of physics involves taking a whole bunch of inputs, different sources of whatever, and running it through some sort of an equation. There's a trick you can use using units to figure out if you're doing something totally wrong before you continue down that path. And that's this. When we use our SI units, which are International System of Units, if I add and subtract two different factors, only identical units can be added or subtracted together. But I can multiply or divide any unit. Think of it like this. Let's say I'm sitting downstairs in my basement. Here's a very attractive representation of me sitting in my basement. I'm just relaxing. And all of a sudden, some raccoons waddle in, which I'm not too happy about. Well, I can count them. 1 raccoon plus 1 raccoon plus 1 raccoon equals 3 raccoons. So as I'm adding these numbers, because the units are exactly the same, I end up with the same unit I began with. Now, let's say to appease them, I offer them cupcakes. And I just happen to have 6 cupcakes on hand. Now, 3 raccoons plus 6 cupcakes Doesn't mean anything. I don't have 9 of anything. What, 9 rack cakes or 9 cupcoons? It doesn't make any sense. But I can divide it. 6 cupcakes divided by 3 raccoons will equal 2 cupcakes per raccoon. So I'm keeping the same unit, 6 cupcakes divided by 3 raccoons, and I get 2 cupcakes per raccoon. I still have cupcakes in the numerator, raccoons in the denominator. So that's the way to always, always, always think about units. Now these same rules apply when you get outside the realm of raccoons and cupcakes and into the realm of physics. Let's say you've solved a problem and you end up with 3 meters plus 2 seconds as your final calculation. I can tell you right now without even looking at your solution, that is incorrect because it's impossible to do. If instead you've got 3 meters divided by 2 seconds, yeah, you can do that. That ends up being 1.5 meters per second. Get this, if you have 3 meters divided by 2 seconds, the units have to be meters per second, which means if the problem's asking for a speed or a velocity, you're probably in decent shape at least. If it's asking for something else, you probably did something wrong. Now, once you start thinking about them this way, they can help you figure out physics problems entirely, actually, which is kind of cool. It's called dimensional analysis. I'll do a quick example and then we'll do a lot more of it in class. Let's say I take Newton's second law, that's just F equals ma. It means force on an object can be determined by its mass in kilograms times its acceleration in meters per second squared. So, if the unit for a force is a Newton, I can use dimensional analysis to figure out what makes up a Newton. I start with F equals ma, and then I plug in what units I know. There we go. And now, since I said in a previous slide, you can multiply or divide any units together, then I just need to multiply kilogram by meter per second squared. I end up with kilogram meter up top divided by second squared below. And that's what a Newton is. And you'll actually find for this entire first semester, everything we do can be boiled back down to mass, distance, and time. Kilograms, meters, and seconds. Everything boils down to just those 3 factors. So if you understand what those are, you can get the rest of it. So we'll practice this a bit in class. Come in with any questions you may have, and I'll see you all there.